My name is Manoj Naik. I'm a distinguished engineer at Nutanix. And today I'll walk you through the architecture that powers our cloud platform, specifically the unified data platform, the design principles, the ideas, the systems that allow us to scale and perform, the way we provide mobility all the way from the edge to the core to the cloud, and how we provide visibility and analytics of user data while at the same time keeping the data secure and compliant. And all of this in support of a true full AI lifecycle. So before I present our architecture, I want to level set the stage on what is available out there today, right? It's as what have companies that provide enterprise storage for traditional unstructured workloads look like, right? There have been these two classic ways of doing enterprise storage. The first one is what is called the shared everything architecture, where essentially you have a cluster of nodes that all have access to shared storage. This shared storage typically has been provided in the past through a storage area network, but more recently through IP-based storage. And then you run a load balancer or some way to direct clients to any of these nodes to provide a single namespace. The idea here looks great because every node has access to all of the storage, so any client can access any node and get access to any of the data. But then, these architectures do have challenges. Data is accessed from anywhere, which means you need some kind of concurrency, some inter-node communication. You need some version of distributed locking to build such an architecture. And for the interconnect between the nodes, you need something that's a fast path for networking between the nodes. That's one. The second one is more of a shared nothing architecture, where you provide a single namespace still, but then you have a collection of nodes that are working independent of each other, right? They're in separate fault domains. They are not typically communicating with each other for providing access to data. But then each node or each piece of this namespace brings along with it compute storage. And then that's how they provide the namespace. This also looks great because it can scale linearly. The domains are different. But then how do you provide a single namespace without having a siloed infrastructure? There's a problem that there's load balancing issues. How do you make sure that specific parts of the namespace don't get hotspots? And so I've, in my past life, worked on both of these architectures. And like I said, both of these have challenges. So what is it that we need to do to break this conundrum that has to work on trade-offs between resiliency and efficiency? So we need a new way that sort of combines the best of both worlds, right? We like the fact that there is accessibility that the shared everything architecture provides, but we also like the linear scaling that we get from shared nothing. And so we want to build an architecture that sort of takes the best of both worlds, and we call this architecture shared flexible. And the idea here is that to provide a global namespace across still a cluster of nodes, but then you're accessing shared storage that's virtual, right? Rather than every node bringing its own storage, the nodes are flexible enough. Some of these nodes can be compute only. Some of these are heavy on storage or a mix in between. But the idea is you want to be able to use storage that is within the single cluster itself disaggregated, right? The compute can scale independent of the storage within one cluster. So typically the disaggregated is now a new buzzword where you separate out the compute and storage into different clusters. But the idea here is that you want to be able to scale your compute and storage within the same platform.
Manoj, comment maybe, Scott Robon, solutional. You can call it disaggregated or you could call it reality.
Yeah.
Like this, I think, reflects most enterprise environments, right?
Yeah.
The endpoints you had before are endpoints and maybe only 2% of the problem.
Yeah, actually, yeah. What I've seen is people have built these architectures, especially around things like unified storage.
Sure.
Companies have been around for 25, 30 years. They've built this architecture and they've sort of improved on it. You still have if you look at the underpinnings of these platforms still remain shared nothing or shared everything.
Right.
And they sort of try to bring in the other properties of the other architecture into them. I think what we've done is we sort of realized this problem early on. I mean, we started 10 years ago. We didn't start 30 years ago building a platform. And so 10 years ago, we realized these were problems already. And so we started out building a platform that already had this from the very beginning. And the idea here is that we want to be able to start small, scale this from like few terabytes to multi-petabytes in a single architecture. The same platform will support all the way from small to large. Okay, so before I go into the details of our platform, I want to set the stage on what our principles are, right? What is it that how did we go about building this architecture? So the first thing is the center of everything that we do, everything we do for performance optimization is data, right? And it's a data-first architecture. So the foundation of our architecture is scale out. We want to be able to start small. As the performance, compute, and workload needs increase, we scale linearly. And when I say linearly, it's not a proposal, right? It's a reality. I mean, we see that you start with a 3-node cluster and increase it to, and I'll show you later in the slides, that performance scales absolutely linearly, right? You can grow compute and storage capacity independent of each other. The other one is about having fine-grained metadata. And this is important because it allows us to smartly place data in our platform. We have tiering all the way from within the platform, from NVMe to SSD to hybrid drives, all the way to the cloud. And we also do intelligent caching and and other ways in which we can give visibility into how the users are accessing the data, which later on allows us to do analytics.
Can you go a little bit deeper into how caching?
Yeah. The other thing is that we do exploit protocol features for data locality. So traditionally, people have built NAS environments to support all kinds of protocols, right? But we've taken the approach of saying that there is advancements in the protocols now. I mean, they've been there for many years, but people have started sort of leveraging them now, right? Things like referrals, multi-channel in the SMB protocol, multiple connections and referrals and PNFS in the NFS stack. And we do take advantages of these. We exploit these protocol features. The idea is that we want to be, yes.
You support flex files under PNFS?
We are in the process of building a PNFS solution. I'll talk a little bit about that.
So you're not PNFS yet?
We are PNFS in development. We'll be there shortly. But we do support most of the features of the V4 protocol, which allow us to do referrals. And I'll talk about, so people have typically, just to answer that question specifically, right? People have done referrals in a way that generally builds namespaces. We have extended referrals to go all the way down to directory levels. And so we can do actually low-level sharding of our data through referrals. And so the idea here is to be able to direct clients to where the data actually is, rather than moving data between the nodes in the cluster.
This is Keith from the advisor bench. Can we ground this in kind of the, some of us are not deep storage people, so we're not always rocking kind of the relevance to the AI, our AI data pipeline. How does this help me in my AI data pipeline?
Yeah, so I think the idea that Vishal set the stage, right? For the data pipeline, as you showed, for the entire life cycle, there are various ways in which data flows through the system, right? So we want to be able to support data that's collected at the edges. And at the edges, they might be a single node cluster, for example, or even very small clusters. As the data flows through the pipeline, I think it lands on data centers in the cloud. You want the same platform to be able to address the data in various places, right? Assuming you want to build a single unified platform for all of your data as it flows through the various cycles. You want to build a system that can work on the edge, can work in the data center, and work in the cloud. The same architecture has to work in all places. The second thing is you want to be able to provide mobility, right? You want the data, assuming that you want the same data to move around. You want the ability to move the data from these places. And the third thing is visibility, right? It's not just collecting data. You want to be able to make sure you have access to that data. and be able to keep it secure, right? So I think the principles here are sort of addressing the idea that data as it flows through the AI lifecycle pipeline is always available, always performant, always secure.
I guess.
And
Go ahead.
I'm sorry, and I think we're missing the critical thing. This is operational consistency, right? So whether I'm edge, data center, or cloud, my underlying data pipeline, at least the storage feature of this, and when we talk about the database capabilities consistently, this is a problem in AI that no matter where my inference, and I'm inference focused, where that's running, that the my operations isn't changing.
Mm-hmm.
That's the question. I'm assuming that that's an outcome that you guys are achieving here.
Yeah, so I think what we are setting the stage for is that the fact that the platform remains the same, whether you run it at the edge, in the data center, or the cloud. I think we are setting the stage that the unified data platform is the same.
And I would say the answer is yes. Like, so the way we are looking at, like, for example, for the inferencing piece, like if you are running a vector database, for that, yes. But you're also looking at, say, a KV cache kind of solution. You want to cache all that inferencing data. That's where some of these high performance, scalable storage becomes very important.
Yeah, so the reason why I ask this question is, as we think about stuff like pre-fill, and if I have a team focused on troubleshooting pre-fill, and we have to go beyond the platform interface, and I need to look at logs, and I need to understand from a performance and telemetry perspective, how do I get the fastest tokens, if that's my goal, out of the system? I'm not changing my SRE process for the edge versus the data center versus the cloud.
Yes, exactly. That's
operational consistency. That's what I mean by operational.
Absolutely, absolutely. Yeah.
Okay, the next thing is we are performance optimized.
Question.
Yes.
To follow on, Keith, there's, from a AI perspective, data orchestration becomes more and more important. And where does this solution fit into that space?
Yeah, let me get to that. I mean, quick.
Good.
Yeah. Okay, so the other thing we wanted to talk about is performance, right? Obviously, performance is important for AI workloads. And we are software defined, so we do not rely on specialized hardware. But, like NVMe drives or, fast interconnects or GPUs, we don't rely on them. But if they are present on the system, boy, we'll take advantage of those. And then, beyond the data first architecture within the cloud, within the data center, we do want to be able to provide mobility, and replication has been something that we built right from the inception of the product. And we are cloud integrated more recently now by being able to run natively in public cloud. And that allows us to move data seamlessly between on-prem and cloud. And the last one is being able to provide data protection and governance, right, with built-in rules that allow us to do this across the stack. So the foundation of our...
And Manoj, when you say data protection, you're talking about snapshotting?
Snapshots, replication, metro, sync, cloud.
Yeah, but you're not doing outboard backup of databases or things of that nature. You're not putting it on some other medium.
No, we're not. We were putting it on our own object store. So we have a built-in object store, but yeah.
That's what I was trying to say.
Along with our data first architecture, we also have a control plane. We want to make sure that our control plane works in concert with our data. We have a unified control plane that is powered by what we call Prism Central that provides a single pane of glass. Whether you're managing one cluster, one site, cloud environments, you get the same control plane. We provide data insights and analytics into data. We're able to detect user patterns, identify threats, remediate them. We are able to convert what we call raw telemetry into insights. We have a lifecycle manager that sort of manages the install upgrade of our entire stack, right? All the way from hardware, if you happen to run ours, all the way to the apps. We support open APIs. Obviously, we want to be part of the ecosystem for automation, the integration with third-party tools and DevOps workflows. We have a marketplace on our Prism Central and Nutanix Central think of it as an app store for your platform. It allows you to switch between apps and gives you visibility into all the apps that we support.
Would this solution work for something like data lakes and things of that nature? I mean,
Yes.
sizable storage
Yeah.
configurations.
Yeah,
on
I'll quickly get to that.
multi-hundred
Yes.
petabytes.
Yes.
Kinds of things.
Yep.
Yeah.
Yes.
Keep
Give me
saying yes.
give me a moment. That's the
Okay.
next slide coming up. Okay, let's talk about scale, just as what you were pointing out, right? We want to be able to, like I said, start small, but scale for capacity and performance, right? So let's see what it means to start small, right? So our clusters can be as small as one node, right? But typically for high availability, you need to run at least a 3-node cluster. That gives us the platform to run on top of. This gives us the ability, the platform gives us what are called containers that provide all the enterprise storage primitives like replication, compression, all of that stuff. And then on top of this, we run our services, right? Our apps that provide the namespace for objects and a namespace for files. And all of these managed through Prism Central. Now, let's say this is a fully featured, resilient solution that can be deployed at the edge. And this is how you would start out if you had a smaller workload. But as the workload grows, you can actually add capacity to the cluster, right? Seamlessly without impacting the applications that run on top, right? And capacity scaling is just a matter of adding more storage to your environment. It's the same cluster, but it scales, right? And similarly, if you want to scale compute instead of your storage, you could just add more service endpoints, right? So for example, in case of an objects namespace, we just add more worker nodes. In the case of files, we would do the same thing by adding more file server VMs. And so here's what the question specifically you asked, right? How can we scale as data grows, right? So if you were building a data lake where you have unstructured growth of data, which is almost relentless, then you can actually scale our cluster to up to 32 nodes within a single cluster, right? Each node in our cluster today supports more than a petabyte, which means that if you have a 32-node cluster, you can have multi-petabytes in a single cluster, right? And of course, you want to go beyond the limits of a single cluster. So if you were building a very large data lake, you can actually present a single namespace across multiple of these clusters, right? So in case of an objects namespace, for example, you can have 128 clusters connected in a single global namespace. And for files, you can go up to 10 clusters in a namespace. And the idea of a namespace here, I think the question was asked earlier about what a global namespace means, right? So the idea is for our clients to be able to access a single namespace, right? So from the NFS, SMB, S3 client point of view, they see one endpoint, right? They see one endpoint, but we'll rely on the clients being smart enough to be able to get redirected anywhere. And this is a federation workspace or a way of letting clients get to where the data is. So in terms of scale, I mean, we haven't even gotten to a point where we can test at the scale that we are talking about, but we can go multi-petabytes in a single namespace.
So getting back to the object global namespace, is that the fact that one bucket can exist across multiple clusters?
With replication, it can, because we do support replication.
So you're replicating the data from one cluster to the same, but it's the same data effectively in all those clusters. Then.
If you want to use replication, but our namespace means that you can actually have your buckets all over the place.
I understand,
but
can you have one bucket span multiple clusters and it's not being replicated?
No, you cannot. But
thank you.
But yeah, you can have one bucket span multiple clusters in a single data center. But it doesn't make sense for you to have one bucket span across clusters that are geographically distributed. But within a cluster, yes, the answer is yes.
You mentioned opposite answers. So you can have, from a latency perspective, if it makes sense to have multiple clusters in a single domain, physical domain, you can do that.
Yes, you can do that.
But if you're talking about extending it across multiple physical domains, it's better to replicate.
Yeah, and we do replicate in those cases, yes.
Is that, Scott Robon, Solutional, is that configurable? Are there, I guess, like, where are you on the slider bar of, I want it all in one place versus I just want to leave it where it is and access it?
Yeah, so the way we define is, we've been coming up with these concepts called infrastructure domains and availability zones and It all depends on the latency between these clusters, right?
And what you need it for application performance, right? So
Yes.
it's going to be application.
But it also depends on how you replicate at the back end. I mean, we do expect for a replication to work, or not replication, but for a single bucket to span multiple clusters, you need latency that is low, right? Milliseconds.
Yeah.
And if we have to rely on replication, we just expect it to be asynchronous. So that's, I think, our clusters stretch across multiple rooms, multiple, in a single data center,
Sure.
but then that's more of a stretch environment, right? But we still expect the latency and the availability to be as you would expect in a data center.
So basically, everything you're talking about is very focused on AI workload and data for AI workloads where low latency is absolutely necessary.
Yes.
And so you're probably going to not err, but lean toward replication to get everything in one place for performance reasons.
If you wanted, yes, a replication to get data local to where it needs to be, yes. Okay, so just like you can scale for capacity, we also scale for performance. So the key point of this chart is to show that our scaling is linear, right? As you add worker VMs or worker nodes or VMs to the cluster, our performance will scale linearly. And next, I want to take you through what our I/O path looks like, right? And what we have done over time to improve the I/O path of a typical pipeline that goes all the way from, so we do support, like I said, NFS, SMB, S3 into the same interface. But I'll take the example of an NFS client accessing data or a flow of data from all the way from a client to our storage. Right, so let's look at what our architecture looks like, or this has been how we've sort of built our platform in the past. There is an NFS client that accesses a service endpoint that we call files, which is part of our unified storage. There is an NFS adapter that runs within files, and there's a file system that talks to so when a request comes in from an NFS client, it's typically TCP, or that's what it's been in more commonly. We use an IP-based networking to connect to storage, and we go over what we call a virtual switch within our hypervisor. And that typically follows a path that goes through the kernel, all the way up to another service that we run on our controller virtual machine called Stargate, which actually provides the storage functionality, right? And this has been the path typically. And then for replication within the cluster for availability, we need to go another path that goes through the kernel again to another node in the cluster, and that's how we get replication within the cluster, like for RF. And this has been what we started with. So the first thing we did was we looked at whether we can do fast path between our storage layers, right? So within Stargate, we leveraged Rocky for providing data plane efficiency. For a replication within the cluster, for metadata operations, we did a fast path between our storage layers. This is all transparent to applications, and that gave us performance boost. The second thing we did is we introduced this feature in our hypervisor called Turbo, which basically is, again, transparent to applications. But it allows us to go a fast path between our hypervisor and our storage stack, right? So it bypasses the kernel on the host machine and goes straight between two user processes that are running on the same node, right? And that we call AHV Turbo, and it provides iSCSI access over RDMA. So that's the fast path on the data path. And then the last thing we've done more recently is to go all out doing RDMA all the way to the client, right? So the path from our service to our hypervisor is now with direct attached storage, right? So we don't go IP anymore, we go direct attached. And we also do RDMA to the client, which allows us to take advantage of things like GPU direct, the client running GPUs and so on, right? So this gives us an end-to-end RDMA path all the way from the client to storage. And we've been successful with publishing our performance with the community, right? So we've been early adopters of the ML Commons MLPerf benchmark that came out of the ML Commons standard. We started interacting with the community. We have a couple of folks who are part of the committee, and they've been working with them since 2023. And so what MLPerf benchmark does, just to give you an idea, is that it it simulates real-world AI/ML pipelines, right? Typically people run storage benchmarks looking at raw I/O throughput, but this actually simulates an end-to-end workflow of a model training exercise. And it measures performance across two of these workloads. One is called ResNet 50, which is more for image classification. It sort of exercises small reads performance. And the other is UNet 3D, which is more for medical image simulation. It exercises large sequential reads and checkpointing, which does heavy writes as well, right? So workloads that sort of work across both sequential and random reads and writes, but not typical benchmarks that you run with FIO. So it actually simulates an actual pipeline. And so, like I said, we sort of participate in this benchmark, and we've been among the top vendors that have published in this space. In last year, we were able to get about 2,100 accelerators. An accelerator is essentially what it takes to keep a GPU accelerator busy for 90% of the time. So the I/O load that you would exercise to get an accelerator busy. We were able to improve this in this year by 2 times. And so we got the same number of accelerators, but we used half the hardware for it, right? So our first solution was with 32-node cluster. The second solution was with a 16-node cluster. We could have gone higher, but you just don't have the hardware with that large. And our per node storage performance has gone up 130%. So key enhancements here are what I described earlier in the slide, right? RDMA all the way to the NFS client. SRIOV we use for near native performance and high performance networking, right? We use ConnectX 7, 8.
Nice. The performance applies to both ResNet as well as UNet 3D.
Yes. So
files, small files, both are performing better with the latest Rev.
Yes.
130% increase.
Yes.
And what you're saying there is how many accelerators you can support.
Yeah. So like I said, it says there 2,300 accelerators right now on a cluster of 16 nodes.
Yeah.
We can go higher, but I'll talk about
These are
that.
like H100.
Yes.
I mean, different. You can have different.
Yes.
Yeah.
So
right.
I don't know the details. A100s, H100s. It's a combination. I think it's.
Yeah.
I think the ResNet is A100 if I'm not mistaken, but I'll have to check. I don't know which ones are.
Yeah. So Dave Graham, ML Commons, the providers of this.
MLPerf.
Yeah, MLPerf is one of the things. Yeah, and one of the things to call out here, and I appreciate your attention to this detail. Like these benchmarks are constantly being revised based on community standards as well. So like the sample that Nutanix is providing here is amazing. This is indicative of a point-in-time snapshot, and this continues to evolve, I think, on a biannual basis anyway as we evaluate it. So actually, I think ResNet 50 is going to disappear in the next benchmark anyway because it's going to be replaced by a different benchmark. But when you start to look at these things, this is exactly why we do this. It allows the individual vendors themselves to take a look at their characterizations on a path forward, ready to reflect your points. Like, yeah, what does it look like on small, medium, and large block workloads? Elephant flows, mice flows, this kind of thing. And how does it impact these pipelines as it goes along the way? And so when you're able to characterize things in this fashion, yeah, you hope for that 200% increase or a 2x increase over what's going on there. So yeah, no, and Nutanix has been a great part in up-leveling the entire industry by virtue of what they're doing here as well, right? They contribute to the understanding of what these benchmarks mean. So it's not just useful to them in their own marketing, which they're not allowed to compare themselves to other people, by the way, which is great.
I can compare
But
to other people.
But you can. You absolutely
If
can.
you give me a benchmark, I'm going to use it. Yeah.
But this, just from a broad brush, I mean, this is exactly what we want to see from this because this shows that kind of tendency to move forward. And if you want the details on some of these benchmarks, we can certainly provide them.
And this is a training solution. This is not inference MLPerf storage, right?
This is the MLPerf storage, right?
Checkpointing activity. You're
Yes.
seeing all the activity that might go on in a typical training solution, but you're not. So inferencing is going to look somewhat different.
It should.
If we ever get to that point. Right?
It should. Yeah, I mean, Nutanix, I can't speak to their their overall participant in each of the groups, but typically as a member, they're able to have impact on the inference and training specific work groups themselves, which have their own discrete benchmarks. So you may see them show up in those particular things, but this is directly onto the MLPerf storage side of the house. So it does try to be combinatorial in workloads to represent as much of that possible.
Right. Manoj, Nick Patience, can I just ask, as you scale, they are very impressive numbers. Where do you see sort of the next bottlenecks coming? If you like, double the amount of accelerators or something like that, is it like file metadata, or is it network fabric? Or?
Yeah, so I think one of the challenges that we've had and that we are working on is the fact that we still want to run on a platform, right? We still want to be software defined. We still have to go through the stack that goes through the hypervisor. So we've been working on some accelerations. For example, virtual functions for our network cards, right? So in this exercise, we took ConnectX 7 and 8 network cards and did pass through directly to our file server VMs, right? So there are some accelerations that we have to do around SmartNICs, things like that allow us to get the same kind of visibility into our service layer that you would not expect typically in a virtualized environment, right? So those have been where we've been working on. Again, we want to be able to, like I said, software work within the bounds of the fact that we want to be software defined. The same stack works in the cloud, right? And in fact, the first benchmark that we did in 2024 was actually running entirely natively in AWS, right? So the 32 nodes that we were able to run a cluster was in AWS, right? Using EC2 instances rather than our hardware, right? Or our platform. It was actually running natively. So we want to be able to, our software needs to be able to stay software defined, or our solution needs to be able to stay software defined, but we do need to be able to take advantage of these improvements that have
Were
come
those
from
on Metal instances, or were you using some other?
No, for the cloud, no,
Yeah.
they are just EC2 instances.
Which GPU?
Yes, no, this is a simulation, right? So it doesn't actually run with
no
GPUs.
real GPUs being burned.
Yeah, so yeah, exactly.
No harmed.
So, yeah,
Exactly.
so you just want to show that, and by the way, in AWS, we can't use RDMA, so we were just using TCP. So the first iteration of ours was just TCP, right? The second one was with RDMA, and that's another reason why we got the acceleration the second time around with half the number of nodes. The first one was just using pure TCP from the clients, right? Okay, so like I said, constantly improving performance. We started out with the first iteration of MLPerf with performance of about 5 gigabytes per second per node. We're at 20 gigabytes per second now, right? With all the acceleration work that we have done. The next thing I want to talk about is it's not just about performance, right? Obviously, in a stack like this, you want to be able to handle things like data safety, mobility, and all of that stuff. And so we do have a complete SLA-based data protection in our stack, right? So this was the questions that came up earlier. What do we provide in terms of data protection? So I think of this as a wheel with every spoke in the wheel providing some form of capability around data protection. The first one is Metro. Metro is essentially being able to synchronously replicate our entire platform from one cluster to another, right? Whatever runs on it, you can pick and choose. You can have the entire cluster replicated, or you can have entity-based replication. So you can pick a subset of your workload with some VMs and your file servers to be replicated to another cluster. This is RPO of 0, right?
Just to make sure, like, you mean like a geographic metro, right? Like,
yes,
with
some requirements, right? You still want under 5 millisecond latency, for example.
Yeah, okay, that's fine.
Yes.
But like not just within a data center.
Absolutely not.
Okay.
Yes. The second one is like snapshots and DR, right? I mean, this is standard, nothing special about what we do, but we do provide, snapshots at the level of a share, and async replications, right? This is happening at the service layer, right? We don't have to take the platform in place. So you don't have to involve the VMs. You can just do at the service level replication.
And the Metro replication applies to object?
It applies to anything that runs on our platform. So you could just say, I want.
So a multi-petabyte data lake.
You wouldn't do it.
Could be replicated across the Metro boundary.
You could, but if you wanted to, but it doesn't make sense to do.
The choices are you back it up or you replicate it. I mean, to a large extent, right?
Yes. And, we do have people who replicate, do Metro in petabytes. We do have customers, maybe not hundreds of petabytes, but yeah, I mean, petabytes we do.
The German customers
Yes,
primarily. Yeah.
we do have customers. In fact, especially in Europe, people will will do Metro for everything. I mean, it doesn't matter how much data they use.
And we are seeing that in the Middle East also. Like quite a few of those deployments are requiring Metro and DR, like the cascading one that you talked about.
Yeah, we will push people to do async replication if it's of that scale, but we do support Metro. So other things like object replication, like I said, we do have our own object store that runs on-prem, but then if you wanted to integrate with an object store in the cloud, like Amazon's S3, you can actually do replication between our object store and the cloud. And then we support things like, for SEC compliance, we have support for object locking and file locking with write-once semantics. And we also do change file backups, right? So our backups work with what we call change file tracking, nothing new. I mean, everybody does it. But we've integrated with our backup vendors. So our backup vendors are able to use our open APIs to be able to do backup using differencing.